kind of blue is the same. You can have an artist who can tell, let's say, 3, 4, 5 different kinds of shades of blue, even 10 shades of blue. Maybe they can differentiate. I myself just say blue, but an artist might be able to tell 10, 15, 20 shades of blue. But remember that when we mentioned absorption of light and the light that gets absorbed by it and the light that gets reflected by something. If it's a color, it's absorbing some light and reflecting other light. Now, the human eye might be able to only differentiate between, let's say, 10 or 20 colors of blue. But the spectrophotometer that knows exactly where it was, what it absorbed, which wavelengths were absorbed and which were reflected, such that it has this shade of blue, that can make a lot more differentiation. Sometimes it can and sometimes it can't. But that's why we use a microspectrophotometer. We put this dye in the microspectrophotometer. We send light through it. We see what's absorbed. We see what's reflected. And we can tell a lot more. We can differentiate between many different kinds of dye, even if they're the same color to the human eye. So this is a way to connect it. So if we, we have a fiber at the crime scene, and we find, let's say the shirt of the victim has a fiber. And we look at that and we see exactly where this blue fiber, let's say, absorbs light and reflects it, or absorbs it and then reflects it, gets it back to the other, the eye. What gets absorbed, what does not get absorbed. We look at that, and then we find a fiber on the suspect. And again, it looks blue, but yeah, everyone has a blue shirt, right? Anyone can get a blue shirt. But we put that thread under the microspectrophotometer. We send light into it, and we find that, lo and behold, this is absorbing and reflecting the exact same colors. So this is a lot stronger connection between the hair find of the suspect, or the fiber of the suspect, and the fiber at the crime scene. And we can connect the suspect to it a lot more. Now, even a microspectrophotometer using ultraviolet and visible light might not be able to differentiate between various blue dyes. A lot of them it can, but some of them it can't. So one of the things that's done is we don't use ultraviolet, we use infrared. Hopefully we'll see about that soon. And that will differentiate between any different kinds of dyes. But if there's a mixture, we can sometimes take the thread, dissolve it, and we use something called thin layer chromatography to break apart, let's say, has 2 or 3 different kinds of blue dye in it. So we can actually find out if there are 2 or 3 different dyes. We'll know, and we'll separate the three, and we'll examine all 3, and we'll take the hair found of the suspect and do the same thing. And if all these things are the same, again, it's a strong correlation if they're all the same. If when you separate the different dyes, they're the same in both the crime scene and the suspect, this is a strong indication that the suspect was at the crime scene. We also check in the microscope. We check the diameter. Different fibers have different diameters, and if the fibers have the same diameter, again, it's not an individual characteristic, because there are other fibers that have the same diameter. Not to mention that the person's shirt. The manufacturer doesn't only sell one shirt to one person. It sells, let's say, 500 shirts. So even if we find this fiber, the suspect, maybe it came from the other 500 shirts. But again, it is a strong it is some form of connection if the diameter of the dye of the thread of the fiber at the crime scene and the diameter of the thread found at the suspect, they're the same. Again, it is it forms some connection. It's not proof, but it makes it more highly probable. Also, we check not only with the cross-sectional shape, and they can be all kinds of weird shapes like this. Round, flat, dumbbell shape, it's like 3-lobed. They might not be common, but if we see them the same at the crime scene and the suspect, we form a connection. Not proof, but again, it forms some connection, and it does help. So we mentioned using a microspectrophotometer with the dyes and what it absorbs. Now, that was with the ultraviolet and visible light. But we have that, and these are easier, these are cheaper devices to use. But we want to use infrared. Infrared, when we want to see what absorbs in the infrared, this is gives very, very specific information as to exactly what compound, what chemical was used to dye this fiber. It will tell you exactly. Now, the other one will tell you where it absorbs. And you have several different chemicals that are that absorb in the same place or near the same place. But infrared, what absorbs in infrared, the way it absorbs in infrared, that is unique to every compound. So if you, so different materials and different dyes will absorb differently. So we can identify a specific material or a specific dye. And again, we're talking about a thread here, so we don't want to just put it inside the infrared thing. We got to make sure that the light and the infrared light is going through the hair. So we need a microscope because we got to focus right on it. So we use they do have IR microspectrophotometers. They're more expensive than the other kind that use ultraviolet and visible light, but they have them. Also, the spectra are a little bit harder to interpret. You can, don't get me started on that, but anyway, in any event, you can, when you match the IR infrared spectrum that you get from this microspectrophotometer, you can identify exactly what the dye was. And this is, again, enables you to make a very good comparison because we know exactly the same dye was used. Again, that forms a good connection. But again, as we mentioned, it's not just one shirt that's sold. You might be able to prove that it is this brand of shirt only that uses that dye and that is connected. That was at the crime scene. It doesn't prove that what the suspect had was from the crime scene. It just proves it was the same exact shirt, the same fiber from the same kind of fiber from the same exact manufactured shirt. So even if you can't, you don't have a suspect, for example, what you can do is when you take the fiber at the crime scene, if you know it comes from the perpetrator, let's say the victim doesn't have any blue shirts, he only has white and blue, and you find the red fibers there. So this must have come from the perpetrator. So what you do is you look at this under the IR microspectrophotometer, you get exactly the chemical used in the dye. So you find out, so who's selling this? Who's selling shirts with this kind of dye? So you find out who's selling it, and you find where these shirts went, and you can narrow down your suspects this way. Like, for example, there's only one enemy of this person's that bought that shirt. So this person becomes a person of interest. We start to suspect him. Again, these are just things you can do with the IR microspectrophotometer when you know the exact chemical the dye is made of. There's another thing. We're not going to go into this too much. Light going through a fiber can be polarized, and it can change the polarization. So you can use a polarizing microscope. We mentioned this when we dealt with microscopes. So you send a polarized light, using a microscope because it's a very small thing. You send a beam of polarized light into it, and you see when the beak line disappears. And we'll see what kinds, put in a liquid, and we'll see what the refractive index of this light is, or we'll see how it rotates the polarized light. So we can use polarized light. We can use the refractive index of the fiber sometimes also for identification. So we'll know exactly what kind of thread, or more or less which kind of thread was used, and we can use it to compare not just the chemical, but also the refractive index or the way it rotates polarized light. Here's an interesting case.